Hello, my name is Kostas Sprigakis and I'm going to present you a work entitled The Use of GVL for the Holistic Valorization of Biomass, and a work that includes process and energy integration techniques for the development of biorefinery scenarios towards the production of platform chemicals. So this presentation starts with the challenges for the holistic valorization of biomass, as well as with proposals for the effective utilization of lignin. Next, we have the aim of this work, as well as the methodology including process flow sheeting, energy and techno-economic analysis. Next, we have the presentation of the energy and economic performance results, while in the end we have the conclusions and some proposals for future work. So there are fundamental incentives to fractionate and exploit biomass components in a holistic way towards the production of a variety of products, while also there are vital challenges related with exploitation of lignin-rich feedstocks, which are actually underutilized due to processing bottlenecks. And in fact, there are important incentives towards the exploitation of the lignin's aromatic content, which is expected to have a significant positive effect on process economics. So the reason why lignin is underutilized is originated to the role of pretreatment, whose main goal is to separate and transfer biomass components by cleavage of biopolymer bonds in between the polymer chains and cleavage of intermolecular bonds within the biopolymer chains. However, in these process conditions, there are vital bottlenecks related with the need of expensive separation technologies to address separation of product mixtures that feature wide structural characteristics that are subsequently increase capital and operating expenses, while in the meantime bottlenecks related with degradation reactions further inhibit separations and reduces yields. So pretreatment commonly occurs at relatively high temperatures, strong acidity or alkalinity environments, and there is a feature effect of lignin related with the cleavage of ether bonds in between monolingols, as well as the spontaneous repolymerization by the formation of carbon-carbon bonds. As a result, we're going to have an irreversible condensation of the lignin structure that results in reduced aromatic monomer yields during subsequent processing. The proposed process aims to successfully extract lignin and is based on the lignin-first concept for the biomass pretreatment to inhibit the formation of carbon-carbon bonds. So in this process, a GVL water mixture is used as a biomass solvent system that is capable to favor selectivity towards the production of useful products, as well as at the same time it's capable to limit degradation reactions for sugars and lignin. In addition, we address the effects of formaldehyde addition, which is capable to react with the newly cleaved sites and consequently inhibit the formation of carbon-carbon bonds between the monolingols. Next, the catalytic hydrogenation of this lignin structure with the use of palladium and ruthenium catalyst will result in lignin aromatics with near theoretical yields of 50%, while similar treatment of the unprotected lignin could typically yield 5 to 20% of lignin aromatics. An additional effect of formaldehyde addition is the protection of xylose. Another major reaction that occurs during pretreatment is the depolymerization of the hemicellulose into xylose and its degradation into furfural in humans. However, the formation of furfural in these states complicates downstream separations as furfural forms an azeotrope with water. So the existence of formaldehyde results in a protected xylose structure, which is that of dimorphyl xylose. The aim of this work is the development of two pilot plant scale biorefinery scenarios towards the holistic valorization of biomass and the production of platform chemicals. Next is the evaluation of the effects of lignin exploitation on process economics, as well as the identification of the most profitable scenario, and finally to set the basis for an expanded product value chain. The methodological approach starts with process flow sheeting of two alternative biorefinery scenarios, where biorefinery A follows a traditional GVL organosolved pretreatment, while in biorefinery B we follow lignin-first approach, where we additionally use formaldehyde in biomass feedstock. Next, we implement energy analysis and total site analysis for the integration among included subunits of each biorefinery case, as well as for targeting of site utilities, while the analysis concludes with results for capital and operational expenses, as well as for the profitability of each scenario. So that is the biorefinery value chain that utilizes white birch as biomass, which is fractionated into sugars and lignin, whereas C5 sugars, and essentially xylose, is transformed into furfural, C6 sugars is transformed into formic acid and levulinic acid, while part of levulinic acid is used for the production of GVL, which is used as raw material back into the biomass fractionation. Finally, aromatics are produced based on lignin. In this work, hardwood biomass, and especially white birch wood, is used, which features high lignin content and a high ether bond content, while GVL is used as an organic solvent. GVL favors selectivity of useful products. It's capable to limit degradation reactions of sugars and lignin, and also features a limited solvent degradation in the selected processing conditions, while finally enables relatively easy separations due to its properties. That is the conceptual process diagram of the two alternative biorefinery cases, where in case A, formaldehyde is not used in the feedstock, while in case B, biomass is combined with 6% of formaldehyde in order to protect xylose and form dimorphyl xylose, which next is dehydrated into furfural. Lignin is hydrogenated into aromatics, and the glucose fraction is depolymerized into levulinic acid. That is the biomass fractionation process based on case A, where GVL is used as solvent in the system to inhibit degradation reactions into humus and furfural. So the results are summarized into the base of 100 parts of biomass, which require 320 parts of GVL, while 81% of C5 sugars is converted into xylose and 95% of lignin is dissolved. Downstream fractionation, water GVL mixture at the ratio of 6 is used in order to effectively precipitate lignin by 82%, which can be next removed by means of mechanical separations, resulting into a thick brown paste, which next can be dried, yielding a brown powder. Next, we have the biomass fractionation process of case B, where formaldehyde is used, which is capable to inhibit the formation of carbon-carbon bonds between the monolingols. In this case, we can notice that we have lower yields of dissolved lignin, that is 61%, compared to that of case A. However, the catalytic hydrogenation of this protected lignin structure is capable to result in higher aromatic yields in a subsequent process stage. In addition, in this process compared to case A, we additionally have a recovery distillation system for the recovery of formaldehyde, which is recycled back to the biomass feeding system. Next, for the case A, we have the transformation of xylitol into furfural. So the process starts with xylose concentration, something that favors process economics in terms of reduced equipment size and reduced energy consumption in downstream distillation columns. While next we have the dehydration reactor for the conversion of almost 90% of xylose into furfural. In the second case of the transformation of xylose into furfural, we have the use of an additional reactor at the beginning of this unit in order to transform deformyl xylose back in xylose, which is next dehydrated into furfural in a second stage. Here, the use of the dimorphyl xylose does not require the concentration of feed, as happened in the previous case, where the concentration was capable to incur additional furfural losses into the vapor phase. That is the unit for levulinic acid production. The process for both case A and B are the same. Here at the first stage, cellulose is depolymerized into levulinic acid and formic acid, while next a part of levulinic acid is driven to a hydrogenation process where levulinic acid is transformed into GVL, which is used and recycled back into the fractionation process, while at the same time the included formic acid is decomposed into carbon dioxide and hydrogen, which is also used into the hydrogenation process. So finally, we have the unit for the production of lignin-based aromatics. Again, the process for both case A and case B is the same. So for the hydrogenation, THF is used as solvent, and on the right we can notice the big effect of the use of formaldehyde for the protection of lignin and thus to the production of aromatics. So in the base of 100 parts of biomass, 9 parts of aromatics can be produced with the use of formaldehyde, while only 3 parts when formaldehyde is not used. So as a result, we can identify the benefiting results of formaldehyde in the production of aromatics, which that production is capable to result in a significant impact in the economics of the overall biorefinery. Next, we have the energy results for the integrated process units of each biorefinery case, while on the right we have the presentation of the energy demands for its utility level, high pressure, medium pressure, low pressure steam, as well as for cooling water, while in the bottom we also have the energy savings due to process-to-process integration among the involved units. In addition, through the site sources sinks profiles, we can identify potentials for the generation of medium pressure steam, which can be used for cogeneration purposes. So, for both cases A and B, there are cogeneration potentials up to 1.5 to 2 megawatts. Next, we have the breakdown of the main energy and economic results for its case, where in case B, we can identify higher energy and capital expenses. However, the formation of higher lignin-based aromatics is capable to result into a substantial increase in the bottom of the table in the profits of the overall biorefinery case of case B. Here we have the breakdown of material costs, where in both cases we can identify the need for less expensive biomass types that should be considered, while on the left in biorefinery A, the cost of THF and hydrogen for lignin upgrade constitutes almost 42% of the total operation costs. So that means that there is a need for cheaper solvent alternatives that should be considered instead of THF, as well as we could say that part of the furfural output could be transformed into THF in order to compensate this cost. While on the right in biorefinery B, upgrading of lignin attributes to 34% of materials cost, including formaldehyde. While in addition, the diluted treatment of xylose in case B requires an increased input of mineral salt in the decanter, which results in the need for cost-effective salt recovery scenarios that should be considered. Finally, we have the net revenues analysis for its product and its case A and B. So in the case of aromatics, the hydrogenation of the unprotected lignin in case A should be reconsidered since it results in negative revenues for case A, while the exploitation of the protected lignin in case B yields an increased profits, which actually constitutes almost 15% of total profits. In the case of furfural production, the concentrated treatment of xylose in case A provides superior process economics, while the mild pretreatment in case B with the use of formaldehyde in the same time preserves the cellulose fraction, which in turn yields in larger amounts of levulinic acid and a higher profits for levulinic acid in case B. So to sum up, biomass costs are responsible for almost half of the total material expenses, while in case A, the exploitation of unprotected lignin for the manufacture of aromatics features a large relative difference in the net revenue in comparison with case B. In case B, the use of the lignin-first approach should be considered as the most profitable option since it results in positive revenues of about $1.3 million per year for a biorefinery capacity of 10 tons per hour. In addition, in biorefinery A, the electricity demands can be completely supplied by means of cogeneration and using middle pressure steam that is generated by the plant, while the biorefinery B, in the case of biorefinery B, additional power energy should be imported by the grid. As a future work, we would like to propose some additional process modeling tasks, like the transformation of furfural into THF, the investigation of alternative solvent systems instead of THF for the hydrogenation of lignin, as well as the investigation of cost-effective salt recovery systems for the Zeiler unit. Next, we would like to optimize utility levels, demands, and cogeneration using the combinatorial methodology of total site synthesis. And finally, we would like to expand the existing value chain by including additional products. Thank you very much for your attention.